Good morning, everyone. Today I'm going to discuss with you the concept related to thermodynamics. Okay, so our today's topic is thermodynamics. Now I am going to tell you regarding some of the concepts of thermodynamics. First, I am going to discuss with you the terminologies related to thermodynamics. That is system. What is system? System is that we are going to observe, means anything that is occurring in the system, we are observing that, and the surrounding is somewhat that is outside the system. Suppose I have this universe. Okay, I have this universe, whole universe. Okay, universe, and here this is my system. The smallest one is my system, and other than system in the universe, this is our surrounding. Okay, system is the part that we are going to observe. So what is system? System and surrounding. A system refers to the part of the universe in which observations are made, and remaining universe constitutes the surrounding. Could you understand? Now, next one is the type of system. There are three types of system that I am going to discuss. Is first one is open system. Open system means what? In which the system, our system, is not closed one. Means here this, for example, we are boiling water. Boiling a cup of water, a glass of water, we are boiling. Okay, and we are not covering it with a lid. Then there is exchange of energy and matter from the system. This is for open system. Okay, so next we are going to discuss, I'm going to discuss with you. See, I have this one open system. There is exchange of energy and matter between the system and the surrounding. This is my system that is in observation, and other than system, that is my surrounding. Okay, got my point? Now, what is closed system? Suppose what I am doing, I have this glass of water, but now I am covering it with a lid. Okay, now I am covering it with a lid. There is exchange of energy through the walls. The exchange of energy can occur through the walls, and but the matter cannot be exchanged. But matter cannot be exchanged. Okay, because we have already cover it with the lid. So this is closed system. So let me tell you, there is no exchange of matter, but exchange of energy is possible. Now the third system is isolated system. Isolated system means this is my system, but we are covering it with the insulated walls. Okay, insulated walls. If we are covering it with insulated walls, then there is no exchange of heat or energy from system to surrounding. Means there is no travel of heat, because this is insulated. These walls are insulated, thermally insulating walls. So there is no exchange of energy as well as matter. Neither exchange of energy nor exchange of matter. Okay, exchange of matter. I hope I am able to give you a glimpse. Okay, next one is, what is the next? State of a system. How we can define a state of a system? See, if I want to tell that a system is in gaseous state and at what temperature, pressure and volume, when we know the system has some pressure, volume and the temperature, then we are defining the state of a system. So you can see, described by its measurable or macroscopic properties. Means what? Macroscopic properties means pressure, temperature, volume. This is the macroscopic property. I hope I am Clear to you? So macroscopic properties that we can determine easily. For example, we can determine pressure with the barometer, volume we can measure by the help of volumetric cylinders, the temperature we can measure. So this is the state of a system. State of system means when we know or we can define all the measurable properties. Measurable properties. For example, temperature, pressure, and volume. A gas is at what temperature, what pressure, and what volume, etc. Okay. Now, the next one is state function. Okay. State function. When the state function means when only depends upon which only depends upon the initial and the final state of a system. Initial and final state of a system doesn't depend upon the path followed. These are those functions which only depends on the initial and the final states but doesn't depend upon the path followed. Okay. So I have this one. For example, I will tell you what the meaning of this. Delta U, delta H. These are two state functions. Delta G is also a state function. Delta S is also a state function. I will explain it to you that what is delta U, what is delta H, delta G and delta S. So all of these are state functions. Now why I'm saying, why this is mentioned that initial and the final state. Okay. Suppose I am taking A point and a B point. Okay, A point and a B point. Take the this is my route that is followed by the system. Means from P1 V1 T1 temperature to P2 V2 T2 temperature. Delta U and delta H doesn't depend upon the path followed. Okay, delta H and delta U doesn't depend upon the path followed. It only depends on the state B and as well as the state A. For example, if delta U I have to write, I need to write U of product minus U of reactant. Okay, because it depends upon the final minus initial. Now, what is path function? These are those functions which depend upon the path followed. Which depend upon the path followed, or we can say whose value depends upon the path followed. Okay. So, for example, W and Q, work and heat. Work and heat are path function. For example, suppose I need to go from A to B. Okay. If we want to calculate the work done or the heat followed, heat in going from A to B, then we need to think about the path chosen. If I am going from this way to this way, this way to this way, and this way to this way. So we have to know that W1, W2, and W3 are different. Means there is no dependency on initial and final state. It depends on the path followed. That if the path is higher, then work done is also be higher. So I hope I am able to give you a glimpse. Okay. Now the next one is extensive property. So this terminology means extensive means that depends upon the amount of substance. Means if the amount of substance is high, then its value is something else. If amount of substance is low, then its value is something else. Means it depend upon the amount of substance. For example, mass, volume, it is going to increase. If we are adding one mass into another, it is going to increase. Volume, if we are adding two volumes, then it is also going to increase. Okay. So this is extensive property. Extensive property, the property whose value depend upon the quantity or size of matter. Means quantity is amount, or the size of matter means how much bigger it is. For example, mass, volume, internal energy, all these are extensive properties. Next one is intensive property, that doesn't depend upon the quantity or the amount of substance. Doesn't depend upon the amount of substance. Amount of substance. For example, for example, we have we have this one: temperature, density, pressure. We have this one: temperature, pressure, and density. This is intensive property. This one is extensive property. So I have done the terminologies, some of the terminologies like open system, closed system, isolated system. Okay, open system, closed system, isolated system, and after that state of a system. So I completed this. So in intensive property and extensive property, I hope I'm clear. So these are some of the examples like temperature, density, and the pressure. Because you don't know whether we know, if I have this room, suppose I have this room, and this room temperature is 25 degrees Celsius. I am going to divide this room into two ways. We are decreasing the amount, we are decreasing the size of this room, but still the temperature remains 25 in both sides, because temperature is an intensive property. Okay, I hope I'm clear. So next one is our internal energy. Now, with the name internal energy, you can understand that internal energy means the energy of the system with all the kinetic energy, potential energy, mechanical energy is all there. Okay, see, this is a state function, and why I'm telling you, why I taught you state function. State function means that only depends upon the initial and the final state. For example, a b, यहाँ से यहाँ a to b. So delta U depends upon the U of B in energy of B minus energy of A. You are always going to calculate the delta U, means the change in internal energy. You can't calculate the absolute value. That is difficult to calculate. Okay. Okay. It is a sum of chemical, electrical, mechanical, or any other type of energy. Now, the next one is work. What amount of work needs to be done by the piston is calculated by this. Okay, adiabatic process in which there is no heat, no transfer of heat between system and surrounding. Now I can explain in the simple language that what is an adiabatic process. Adiabatic is a process, adiabatic system or adiabatic process in which heat exchange between the system and surrounding is zero. Heat exchange between system and surrounding is zero. Okay. Now we have work done. Actually, internal energy, according to first law of thermodynamics, I will tell you what is first law of thermodynamics. Thermodynamics. Delta U is equal to Q plus W. Delta U is equal to Q plus W, and from that we can say that delta U is equal to W adiabatic, because in the W adiabatic Q is 0, means in the adiabatic condition heat exchange is 0. So that's why delta U means the change in internal energy is equal to the W adiabatic. Now the next one is heat. See, Heat is a change in internal energy of a system by transfer of heat from the surrounding to system, or a vice versa, without expenditure of work, because we are doing it differently, separately we are doing it. So work I have explained you, because if Q is 0, then work adiabatic is equal to delta U, and the heat is the transfer of energy from system to surrounding, or surrounding to system to surrounding, or surrounding to system without any change in work, any exchange of work. Okay. Now, the sign conventions related to work and heat. There are some of the sign conventions that we need to remember. If heat is absorbed by the system, it is absorbed by the system means the heat is going from surrounding to system. Then the heat you need to take in the positive way. If heat is released from the system, or it is absorbed by the surrounding from the system, then you need to take the sign of the heat as negative. For example, if I tell you that Q means heat is absorbed by the system, 25 kilojoule of heat is absorbed by the system, then you need to take the sign of the heat as plus 25. If I am saying that heat is released by the system, 25 kilojoule of heat is released by the system, then Q is equal to minus 25 kilojoule you need to take. Similarly, if work is done on the system, then you need to take the sign as positive. If work is done by the system, means the system is doing work on the surrounding, then you need to take the work as negative. I hope I am clear to you, because if I'll say that 25 kilojoule of work is needed to be done by the system, then by the system it's negative, means minus 25 is the work value, and if uh, mm, 25 kilojoule work is done on the system, then plus 25 is the value. Okay, next one. Now I have done this. Delta U, U2 minus U1 means the second state minus first state, W adiabatic. Heat I have completed, means the positive and the negative sign. And the first law of thermodynamics, the energy of the isolated system is constant. Okay, so these are some of the terminologies that I want to explain you. Now, again, the first law of thermodynamics. The first law of thermodynamics states that total energy of the system remains conserved. Means energy can neither be created nor be destroyed, but it can be converted in from one form to another form. So this is our first law of thermodynamics. And according to this law only, states that energy can neither be created nor be destroyed, but transferred. Okay. So delta U is equal to Q plus W. This is for first law of thermodynamics for an isolated system. Isolated system. Now the next one is reversible process. Now what are reversible process? Reversible means, suppose I want to go from this point to this point, and I am at this position, means at some pressure, volume and temperature. I am uh, I am changing this point P1 V1 to P2 V2 with a small change, a very small change. Then it can be reversed back. Reversible change means it can be reversed back because we are doing it infinitesimally slow. Means if we are increasing pressure, volume, temperature, then by the reverse process, by decreasing pressure, volume or temperature, we can revert to the same state again. Okay, this is an infinitesimal small change. The process which can be reversed at any moment by an infinitesimal change is called a reversible process. Now, the next one is irreversible process. This is reversible condition, irreversible process, that we are doing it at a constant pressure. We are not providing the infinitesimal small change for the irreversible process. We are just increasing a lot of pressure. For example, if I want to go from A to B, I am just decreasing or increasing the pressures at a not at a constant rate, but at any rate. Okay, so that is irreversible process that we cannot reverse it back. Okay, we cannot reverse it back, and it's a fast process. This is a slow process. This is a fast process. Fast process. Okay, so this is reversible and irreversible. Now the next one is, okay, at constant pressure. See, work done. If I'm going to explain the work done formula, that is minus P external dV. This minus is conventional that we are going to use, minus P external dV, and dV is what? V2 minus V1, means final volume minus initial volume. Now we need to think at constant pressure. What is at constant pressure? The work done in a reversible constant, sorry, constant, not constant pressure, it's a constant temperature. If it is a constant temperature, then in the isothermal condition, what we are going to do? In the isothermal condition, means at a constant temperature, we are going to choose this work done in a reversible process and work done in an irreversible process. Okay, I hope I am able to give you a glimpse. For the reversible process, if I want to calculate for the reversible process, you will need to remember this formula. W reversible is equal to minus 2.303 RT log of V2 by V1. V2 by V1. nRT minus 2.303 nRT. N is number of moles. If they are going to tell you regarding the number of moles, then you need to put the number of moles here. R is universal gas constant, universal gas constant, and T is temperature. T is temperature. V2 is final volume, final, and V1 is my initial volume. Okay. So for work done in a reversible isothermal condition, we can calculate by this formula. Work done in irreversible process, we can calculate by minus P external dV formula. Okay, and work done in an adiabatic condition where Q is equal to 0, because I have already explained to you that Q, if heat is 0, heat exchange is 0, then delta U is equal to W adiabatic. W adiabatic. Okay, so this is in the adiabatic condition. For the adiabatic change, we have covered for the this one at constant temperature. Okay. Now the next one is, our next question is 1 minute, and we have this 9th. We have 8th section we covered. Now the 9th one is, okay. Now see, delta U, I told you the change in internal energy. Actually, it is at constant volume. It is at constant volume, So, as we all know that in the laboratory, most of the reactions we are going to do at constant pressure. So for that, we need another state function, which is enthalpy, which delta H is measured at constant pressure and temperature. So for the laboratory purpose, we need to use this constant pressure and temperature. And we can relate this enthalpy to delta U like this. Delta H is equal to delta U plus P delta V. Okay, this is another state function, and we can calculate delta H is equal to delta U plus P delta V. And there is another formula for calculation of delta H, like delta H is equal to delta U plus delta NG/RT. Actually, PV is equal to nRT because this is ideal gas equation. Ideal gas equation. Now, what is delta Ng? Delta Ng is number of moles of is equal to number of moles of gaseous product minus number of moles of gaseous reactant. Okay. Okay. So these are some of the formulas and the important ones for the exam point of view. So now the enthalpy change, if the enthalpy change is negative, means delta H of is delta H is H of product minus H of reactant. If H of reactant is greater than H of product, then the delta H value will be negative. Okay. If delta H means HP minus HR, delta HR is less than HP, then that will be what? That will be positive. Okay. So for the negative, if delta H is negative, we can say that it's an exothermic process. Exothermic process. If delta H is positive, it is an endothermic process. Okay. See. So we have covered this. Delta H is negative, it's an exothermic process. Delta H is positive, it is an endothermic process. Okay. Next, what is enthalpy of a reaction? The enthalpy of reaction can be defined as the change in energy when a reactant is converting into product. At constant temperature and pressure. And how we can calculate this enthalpy of reaction? We can always calculate the change in, because this enthalpy depends only on the initial and the final state and not on the path followed. Okay, delta reaction. Okay, delta reaction, we can write it like this. So we need to see the summation of products with the coefficient in front of it minus summation of reactants with the coefficient in front of it. For example, I have this AA giving BB. This is my reaction. So how I can write the delta H reaction? This is a coefficient, so B. Suppose I have another product also there. Here another reactant is also there, D. So if I'll write delta H of product or the product enthalpies, so I need to multiply this coefficient with the product. Product? Okay, so this is my HP. This is the enthalpy of B plus summation means the sum of the enthalpy of B and C. C into enthalpy of C minus A into, these are my reactants, A into enthalpy of A plus D into enthalpy of D. Okay, so this is enthalpy of a reaction. Enthalpy of reaction we have covered. Now, what is standard enthalpy of reaction? Standard of enthalpy of reaction means when we using the standard states of the reactant or the product. When we are using standard states of reactant and product. And what are standard states? What are standard states? Standard state means when it is, when our element or any gaseous product or reactant is in their standard state. Standard state will be at any specified temperature, for another for an element, the temperature can be any one, but at 1 atmosphere. At 1 atmosphere. If I'll explain to you the more standard state, for example, for iron is in its standard state when it the temperature is 500 Kelvin and the pressure is 1 atmosphere. So the temperature can be anything, but the atmosphere remains the same, means the pressure remains the same. For example, ethene, let me take, suppose ethene has its standard state at 298 Kelvin and 1 atmosphere pressure, means the pressure remains the same, but the temperature can be anything. Now, if the element is in its standard state, then we are going to take its enthalpy of formation as zero. Enthalpy of formation as zero. If element is in its standard state, okay, I'll tell you when we are going to take the enthalpy of formation as zero. So the standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard state, means the product and reactants are in their standard state. Okay. Now, what is standard enthalpy of formation? Standard enthalpy of formation means when 1 mole of a substance, remember this is important, that 1 mole of a substance is formed from its standard state, constituent standard state or constituent elements in their standard states. In their standard states. Okay. So I can say if I want to form ammonia, if I want to form 1 mole of ammonia, then I need to take nitrogen as N2, okay, because I want to have only 1 mole, okay, half of N2, so that it's 1 only, 3/2 of H2. So I am making this reaction so that I help you to understand that how 1 mole of ammonia is forming from its constituent elements in their standard states. Okay. So they see standard molar enthalpy of formation delta RH naught is the standard enthalpy change for the formation of 1 mole of compound from its element in the most stable state. Most stable state is almost a standard state. Okay. So next one is enthalpy of fusion. This is nothing but the change in energy when 1 mole of solid is melted into liquid form. Melted into liquid form. So this is enthalpy of fusion. So how I am going to write it? Standard enthalpy or the enthalpy of fusion is equal to the enthalpy of the liquid state minus enthalpy of a solid state. Okay, so this is enthalpy of fusion. Enthalpy of vaporization when 1 mole of liquid is vaporized into vapors. For example, delta H of vaporization we can calculate by vapor or gaseous state minus delta H of a liquid. Now, what is the enthalpy of sublimation? Sublimation means directly conversion of solid into the gaseous state. But we need to take for the sublimation, delta H of sublimation, we need to use delta H of fusion plus delta H of vaporization. Okay. So this is a concept. So we have this enthalpy changes during the phase transformation. Phase transformation like solid to liquid, liquid to gas to um, gas to again solid can be there. But like delta H of sublimation, delta H of vaporization. So molar enthalpy of fusion or the standard enthalpy of fusion, the enthalpy change accompanies when melting of 1 mole of a solid in the standard state. Vaporization or molar enthalpy of vaporization is the amount of heat required to vaporize 1 mole of liquid at constant temperature and under standard pressure. Uh, then the sublimation I have defined it to you. Okay. So we have this one. So next slide is standard enthalpy of combustion. What is standard enthalpy of combustion? When 1 mole of a substance combusts in the presence of oxygen. So that is the standard enthalpy of combustion. When 1 mole of a substance combusts in the presence of oxygen. Combust means burn in the presence of oxygen. In the presence of oxygen, the amount of heat released during that time is called standard enthalpy of combustion. So we have this one. Standard enthalpy of combustion is here. Delta RH is the enthalpy change when it undergoes combustion and all the reactants and products are in the standard state. So for the standard thing, you need to take the substance in the standard states. Okay. Next one is lattice enthalpy. Now, this is the amount of energy released during the formation of during the formation of substance. Okay, during the formation of substance from their standard states, from their formation of substance, from their isolated gaseous ions. Isolated gaseous ions. Okay. So we have this one. We have what? We have here lattice enthalpy. Lattice enthalpy, it is the enthalpy change when 1 mole of ionic compound dissociate into its ions in a gaseous state. We can say that. We can say that this is the amount of energy released or the amount of energy required, amount of energy the same, only the difference is in the sign convention. If it is releasing means the negative, it's an exothermic. If it is absorbing, amount of energy required to break required to break 1 mole of gaseous compound 1 mole of gaseous compound into its constituent ions, constituent ions. Okay, ions. So it will be positive. So it will be positive. This is our lattice enthalpy. Lattice enthalpy. Now what is the next one? This one is enthalpy of solution. This one is enthalpy of solution. Enthalpy of solution. Let me take the another slide. Enthalpy of solution. This is nothing. Enthalpy of solution is nothing but the amount of energy released when 1 mole of a substance is dissolving in a solution. And the energy released when 1 mole of a substance is dissolved in a specified amount of a solvent. This is enthalpy of a solution. I hope I'm clear to you. Now the next one is Hess's law of constant heat summation. Hess's law of constant heat summation means when we are suppose I want to go from A to B. This is my step that I want to go to A to B, and the delta H for the reaction is this one, delta H. But I can choose a different path to go from A to B. I can go to C, and after that I can go to D, and from D to B I can go. Okay, so what Hess's law says that whether we are going from A to B in one step or in a number of steps, the enthalpy change is same. Means if I put the delta H of reaction, and here I am going to put the delta H1 for this one, delta H2 for this one, delta H3. So my delta H of the reaction will be delta H1 plus delta H2 plus delta H3. So this is the whole equation. Delta H of reaction will be delta H1 plus delta H2 plus delta H3. So what is Hess's law? It is if a reaction takes place in several steps, then the standard enthalpy of reaction is the same sum of the standard enthalpy of internal reactions into which the overall reaction may be divided at the same temperature. You can see this. Okay, you can see this. The standard enthalpy is equal to the sum of the several steps of enthalpy of a reaction. Okay, so this is one. Next one is 15th is heat capacity. Now, what is heat capacity? From the name itself, it suggests that the capacity of a substance to have the heat in it. To have the heat in it. This is the amount of heat required to raise the temperature of a substance, by 1 degree. Raise the temperature of a substance by 1 degree. So heat capacity, the symbol of heat capacity is C, and we are putting the formula Q by delta T, means the delta T, the raise of the temperature by 1 degree. C is equal to Q by delta T. Now what is Cp and what is Cv? Cp is the amount of heat at constant pressure by delta T. Cv is the amount of heat at constant volume by delta T. So this is Cp and Cv formula. Okay. Now, for an ideal gas, there is another formula and there is another relationship that you need to remember, that Cp minus Cv is equal to Nr. This is the number of moles and this is universal gas constant. Okay. So this is N is the number of moles, and the Cp and the Cv. Cp is the heat capacity at constant pressure, Cv is the heat capacity at constant volume. This Qp is delta H, this Qv is delta U. Okay. Next one is how we can measure delta H and delta U for the reaction. So for measuring the delta H and the delta U values, for measuring, so delta H can be measured by calorimetry and delta U can be measured by calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter immersed in a known volume of a liquid. So delta U, what is delta U? The energy changes are measured at constant volume and no work is done. Delta H measurement, it's an exothermic process. Heat is evolved. Then the Qp and the delta HR for the reaction will be negative. In the endothermic process, I have already covered the delta enthalpy of reaction is positive. So this is for the measurement of delta H and delta U, because we can measure the delta U and delta H value with the help of calorimetry. Okay. And we can use calorimeter for measuring delta H and delta U. Now, what is enthalpy of atomization? What is enthalpy of atomization? Suppose I want you to understand what is enthalpy of atomization. The enthalpy of atomization, the enthalpy change on breaking one mole of bonds completely to obtain atoms in the gaseous phase. Atoms in the gaseous phase. For example, CH4. If I want to, there are four bonds CH4. Matlab CH, there are four bonds. I want them to completely change into carbon and the four of the hydrogen gaseous atoms. Okay, four of the hydrogen gaseous atom. This is the amount of energy required in breaking one mole of bonds to obtain the atoms in the gaseous phase. Okay, next one is bond energy. The enthalpy of reaction if we have given the bond energy. Okay, enthalpy of reaction if we have bond energy with us. For example, I want to calculate, suppose I have this one C2, for example, I have N2, 3H2, 2NH3, and I want to calculate the enthalpy of reaction for this, and they have given me the nitrogen triple bond energy 946, for example. For the hydrogen bond, it's 326. I am taking this random value, nitrogen and hydrogen as 236 kilojoule per mole. So I have told you that enthalpy of reaction I am going to calculate by this enthalpy of product minus enthalpy of reactant. Enthalpy of product minus enthalpy of reactant. Okay, so enthalpy of reaction can be calculated by bond energy of reactant minus bond energy of product. You need to calculate by this formula, bond energy of reactant minus bond energy of a product. Now, how I can use this? How I can use this? We have bond energies of reactant. These are our reactants. I need to use. This is nitrogen bond, only single bond. So we need not to multiply it with any coefficient, or you can multiply it with one. Then there is no problem. N triple bond N energy plus 3 into, because this is the coefficient and this is hydrogen bond, hydrogen bond energy minus 2 into, see, there are 3 NH bonds, 3 NH bond here. So I need to multiply this 3 into 2, then it will be 6 nitrogen hydrogen bond energy. Okay, so for that, if I want to calculate, I am going to give you with the another slide. So I have nitrogen value as 946. So 946 my enthalpy of reaction plus 3 into 326, 3 into 326, and minus this, these are my reactants, minus 6 into what? 6 into 236. So by calculating this, you will get the answer. Okay, 946, this is 318, 6, 7, and 976, minus 6, 636, 3, 18, 18, 3, 21, 2, this is 12, 12, 14, 946, 978, 14, 11, 12, 90, minus 1416. 14 minus 6 is 8, 0, and 50. 508 will be our enthalpy of a reaction if it is in kilojoule per mole. Okay, so this is a bond enthalpy. For calculating the bond enthalpy, we can use this formula. Next one is this one. Now, the second law of thermodynamics. Second law of thermodynamics. What is second law of thermodynamics? why we are using this second law of thermodynamics when we have the first law of thermodynamics. According to first law of thermodynamics, it is saying that energy can neither be created nor be destroyed, but it is going to convert from or transfer from one form to another form. But first law of thermodynamics cannot tell us the direction, the limitation of thermodynamic limitation of first law of thermodynamics. It doesn't tell us about the direction of the heat transfer, whether it is going from cold to hot, heat transfer, whether it is going from cold to hot or hot to cold. Okay, so it doesn't tell us, but the second law of thermodynamics tell us about this. Okay, second law of thermodynamics tell us that all the spontaneous process are accompanied by net increase in entropy. The spontaneous process, if there is a spontaneous process, now what is the meaning of spontaneous process? Spontaneous process that occurs by itself. Spontaneous process means that occurs by itself. Occurs by itself, and non-spontaneous occurs by itself. Or you can say a feasible process. A feasible process. A non-spontaneous process. Spontaneous process that doesn't occur by itself. That doesn't occur by itself. Okay, so it's a non-feasible process. Means for the second law of thermodynamics, always there is an increase in entropy. Always there is an increase in entropy, or all the spontaneous process are accompanied by the increase in the entropy. Now, what is entropy? I need to tell you what is entropy. Entropy means the randomness. Entropy means the randomness. Means if there is increase in randomness, then the spontaneous process occurs. This is the first explanation for the spontaneous process. But we are not this is not the complete. We are going to explain this. I am going to explain this by delta G value. Delta G value. Now, the entropy means randomness, means the disorderness, or you can say disorderness. Okay. So the change in entropy. Next, for the entropy, it's a state function. It's a state function. Now, what was state function? Whose value depends upon the initial and the final state. And not on the path follow. So delta S is S of product minus S of reactant. Okay. Another formula for the entropy change is Q reversible by del T. Q reversible by T, it's an absolute temperature. It's not a change in temperature, it's an absolute temperature. Q reversible by T, or delta S total means the total entropy of the universe is equal to the entropy of system plus entropy of a surrounding. Okay, so we can calculate the total entropy of a universe by calculating the system and the surrounding, change in system entropy and change in surrounding entropy. So I have covered this one, and this entropy change. Okay, I hope I am clear to you. Now, next one is Gibbs free energy. Gibbs free energy. Gibbs free energy means what? See, when a system is in its minimum energy, then it has its maximum stability. It has its maximum stability. Okay, so maximum stability. Okay, for the delta G should be negative for them. Delta G should be negative for them. Okay. Uh, Here, if the delta G is negative, then it's a spontaneous process. If delta G is negative, it's a spontaneous process. If delta G is positive, it's a non-spontaneous process. Non-spontaneous process. Okay, if delta G is negative, it's a spontaneous process. If delta G is positive, it's a non-spontaneous process. Spontaneous process means feasible process. Non-spontaneous process means not feasible process. Spontaneous process that occurs by itself. Non-spontaneous process that we need to provide um, some outside energy to have that process. Okay, there is formula for the delta G. Delta G is equal to delta H minus T delta S. Now, what is delta H? Change in enthalpy. Enthalpy. T is temperature. Delta S is change in entropy. Change in entropy. This is change in Gibbs free energy. Okay. Okay. The next is third law of thermodynamics. Okay. Third law of thermodynamics is nothing, not that much we need to require. The entropy of a pure and perfectly crystalline substance at absolute zero temperature is zero. The entropy of a pure and perfectly crystalline means there is no randomness. Our system is arranged like this, means it is pure and perfectly crystalline. Crystalline means in the solid state. If it is in perfectly crystalline, then the entropy of this substance is zero. You need to consider it as zero. Entropy is zero. Okay. So there is no slide. Another. Okay. So I am just going to recap it. First, we have discussed the different terminologies, the open system, closed system, and isolated system. I told you what is system, that is in observation. Open system means there is no exchange of energy and the matter. Closed system, if there is no exchange of matter, but the exchange of energy. In the open system there is exchange of energy and the matter. In the isolated system, when there is no exchange of energy and the matter. Then we have discussed the state of system that we are going to define with the pressure, volume and temperature. Then the internal energy. The internal energy means all the energies that is there in the system, means the electrical, chemical and the mechanical energies. This is internal energy. After that, the work done is work adiabatic. I have explained to you. Then the first law of thermodynamics formula, delta U is equal to Q plus W. After that, we have covered path functions, state functions depend upon the initial and final state. Path function depend upon the path followed. Next, the extensive properties that depends upon the amount of substance. Intensive property that doesn't depend upon the amount of substance. So after that, first law of thermodynamics, neither be created nor be destroyed. What is energy can neither be created nor be destroyed. Reversible process and irreversible process. After that, at constant temperature, work reversible and work irreversible formula. Work reversible minus 2.303 nRT log V2 by V1. In the irreversible condition, minus P external dV. Work done in an adiabatic condition, Q is equal to 0. After that, 9, we have enthalpy change. It's a state function. It's an exothermic endothermic process. Okay, you need to remember these sign conventions. Next one is how to calculate the enthalpy of reaction, what are standard enthalpy of formation, enthalpy of reaction, what are standard state, and for that standard enthalpy of formation is 0. Okay, so I want to tell you that if I took O2, H2, N2, F2, Cl2, Br2 in the liquid state, I2 in the gas, I2 in the solid state. For all these elements, enthalpy of formation is zero because they are in their standard states. If the element is in their most stable standard state, then enthalpy of formation for those substances you are going to take it as zero. Okay, and for the carbon graphite too, it's zero. For iodine solid, for the gaseous state, it's zero. Okay, thank you.